My name is Kia Elison, and my co-author is Dr. Stephen Jones. Our presentation is Students' Multi-Sample Distribution Misconception about Sampling Distributions. The sampling distribution, which I shall refer to as an SD, is of critical importance in statistics. The SD forms the conceptual basis of much of elementary statistics, including confidence intervals, hypothesis testing, and correlation testing. As demonstrated by this graphic from Triolla's 2010 publication, the basic idea of an SD is that given a fixed sample size n, if all possible samples of size n are taken from the population, then the statistic of interest from all those samples creates a distribution in and of itself. It's important to note that the SDs are theoretical in nature. By this we mean that they do not need to be empirically constructed in order to be used in statistical analysis, because the central limit theorem will guarantee all the necessary properties. Oftentimes, simulations are used as a tool to teach students about sampling distributions. These simulations are meant to show the emerging properties concerning the shape, center, and spread of the SD. Because simulated distributions are not perfect representations of the theoretical sampling distribution, Watkins saw that students were sometimes misled by simulations. They observed students who incorrectly believed that the mean of the SD got closer to the population mean as the sample size increases. However, the reality is that the mean of the SD will be exactly equal to the population mean, regardless of sample size. The misconception we discuss is related to what Watkins observed and could even be a root cause of it. Lipson noted that there is a cognitive jump between conceptualizing an approximation of an SD and conceptualizing the full theoretical SD. Taken together, this literature shows that simulations can be a useful tool in statistics education, but they must be used carefully. The theoretical perspective for our study uses Fard's idea of a process versus an object. In short, a process refers to an activity that can be conceptualized as being carried out. An object is the encapsulation of a process into a single cognitive entity. Sampling distributions inherently deal with the process of repeated sampling. That is, an individual can conceptualize taking a sample and recording its sample mean, and then getting another sample and recording its sample mean, and so on. However, the full comprehension of an SD is to realize that this process can be encapsulated into a final result. The result will be the distribution of all sample means, or proportions. Thus, the SD is the object that results from the process of repeated sampling. Students for our study were recruited from an undergraduate course called Teaching Statistics and Probability. The course was designed for pre-service math teachers who had previously completed a course in introductory statistics. 5 students were selected to participate in 2 interviews during the semester. During those interviews, students were asked to design their own hypothetical study and to explain aspects about confidence intervals and SDs. Most incorrect statements about SDs seem rooted in the same misunderstanding. Once we singled out this misunderstanding, we went back to the interviews to try to identify where the misconception came from. In doing so, we saw an important likely connection to a simulation activity performed in class, like those that we discussed in the literature review. Finally, we tracked the students' evolving conceptions of SDs over the interviews. This aided us in identifying what might help to resolve the underlying misconception. Results. First, I will begin with an example of evidence of the misconception. This excerpt was taken from an interview with Corinne, who said, "If you took a bunch of samples and you found their mean, you would get a sampling distribution." I asked her how many samples, and she answered, "More than 30. She believed she was describing a sampling distribution. However, SDs contain not just more than 30 samples, but specifically every single possible sample of size n. Although only one sample is necessary to do statistical analysis, most of our students described that to carry out their hypothetical study, they would need to take many samples to create an SD, as seen in the following statements. The students respectively chose to take 30 samples, 100 samples, 200 samples, and even 1,000 samples to complete their hypothetical studies. That is, they did not conceptualize a theoretical SD with the properties guaranteed by the central limit theorem. In fact, at one point, Ethan suggested that all possible samples really meant all the samples it was possible for someone to practically take in their research. Our research identified and defined the misconception that the SD is composed of multiple samples, rather than of all possible samples. We call this the multi-sample distribution, or MSD. We claim that the MSD misconception is closely connected to perceiving only the process part of the SD. In this way, the MSD is not wrong, but it is incomplete in a critical way. The students even seem to understand that this process could continue with more samples to create a better MSD, but they typically did not understand that the process has an end result that is the SD. We observed two possible origins of the MSD misconception. First, in class, the students generated many samples, computed each of the samples' means, and then plotted them together. This literally builds an MSD. We noted that Tiana recounted this simulation activity and explained that she understood the image she saw of the multiple sample means plotted together as being the SD. Further, Corinne explained that practically speaking, in order to do statistics, one would need to generate many samples and create the type of distribution she saw simulated in class. Second, one property of SDs given by the central limit theorem is that if the common sample size is sufficiently large, often this is given as n greater than 30, then the SD is approximately normal. However, in the simulation, the students saw that with each additional x bar they plotted, the distribution began to resemble a normal distribution more. They therefore confused the size of the sample with the number of samples taken. For example, when Ethan was explaining his hypothetical study, he settled on wanting to collect 30 samples. I asked, "Why is 30 a magical number to you?" He said, "Because the central limit theorem wants 30 samples for the sampling distribution to be normally distributed." We will now discuss possible resolutions for the MSD misconception. I asked Danielle which of her x bars she would choose to compute the confidence interval in her hypothetical study. She said she could choose any of them, but then considered that the most accurate choice would be to take an average of her x bars. She realized that she would be treating her several large samples as one single sample. Then, by thinking of just this single x bar, she began to create for herself the ideas of an SD. Danielle sketched the population distribution, and by reasoning with only a single sample, she began to think more theoretically about where an x bar from a single sample could be in relation to the population mean. This theoretical thinking seemed to help her imagine all possible samples, without having to literally collect all of them. Her resolution was evident when she said, "So, if you could possibly take every single sample of that certain size, and you were able to plot that, the sampling distribution would be normal. And so since that concept is true, then we can just pull one sample point and it will be a point from somewhere on the sampling distribution." This process for resolving the MSD misconception also occurred with Corinne, with some evidence for Ethan as well. In conclusion, we promote simulations as a useful way to develop the process of creating an SD, but claim that instruction must at some point move on to encapsulating the object of an SD. Based on our limited study, we have two suggestions for instruction. Their effectiveness may be a topic for further research. First, it seemed important for some of our students who resolved the misconception to reason more theoretically about the distribution of a single hypothetical x bar. This led to where multiple x bars and eventually all x bars might be distributed. Second, it was also important for our students to explicitly confront the difference between the sample size and the number of samples. To connect our study back to the literature, our study shows that bridging the gap discussed by Watkins and Lipson comes through extending the MSD process understanding to a completed object understanding of SDs. Our study also has important connections to previously reported misconceptions, because the previously observed misconceptions might really be a symptom of an underlying MSD misconception. For example, Watkins explained that some students believe the center of the SD is only approximately equal to the center of the population. This is an accurate belief when applied to the MSD, but not to the SD. In resolving the MSD to the full SD, the students in our study recognized the centers should be exactly equal. Thus, we believe that resolving an MSD into a full theoretical SD may have beneficial consequences in addressing other misconceptions too. Thank you.